In this video, we are continuing with indeterminate products and L'Hopital's rule. So in this video, we'll be demonstrating how to apply the skills that we learned on the previous video on indeterminate products. So then here we are asked to determine the limit of x times ln x as x tends towards 0 on the right hand side. So then here we have a video of ln x, and then we have here a video of x. So we see that as we approach 0 from the right side, this graph turns towards negative infinity. So essentially we have the limit as x tends towards 0 on the right hand side of x ln x is then 0, because if we're looking at this at x, as we move towards 0 on the right hand side, x then goes to 0. So then we have here x 0 times, and then as we've said once again, that approaching 0 from the right side, ln x goes to minus infinity. So then now you see we have a case of 0 times minus infinity, which is an indeterminate form. As we've demonstrated on the previous video, whenever we have such a case, then we need to try to express this product in this form. And I need to highlight to you that it matters what value you choose to put it at the denominator, because that will determine the ease of solving or differentiating thereafter. So I'll show that in a moment. So what we need to do is we need to try and convert this into a 0 over 0 or slash infinity over infinity. So then let's first then convert this into this case, and then if we have this case, we know that we should be able thereafter to apply L'Hopital's rule, because L'Hopital's rule requires that we have such cases. So then let's write the limit as x tends towards 0 on the right hand side of x ln x, so is equal to the limit as x tends towards 0 on the right hand side. In this particular example, we'll choose this to put at the denominator, and we'll choose to keep this, so we'll have ln x, and then we want to put this in the denominator, so we'll have 1 over x. Notice that the 1 over x is important, because we want to make sure when we simplify this we get the same expression as previously. So then we have this. Now if we try to draw now this new expression, because now we have this expression and this expression, right? So let's draw ln x once again. If we draw ln x, we will have this, right? But if we draw 1 over x, do you see we have a new expression of that? And remember that we are determining the limit as x approaches 0 from the right. Once again, we see that ln x approaches, as we move from right to the left towards 0, ln x approaches minus infinity once again. But now let's look at what happens to 1 over x as we approach 0 from right to left. Then we see that as we approach 0 from the right, then this goes towards infinity. So now do you see we have a case of infinity over infinity? Then this means that we are able to apply L'Hopital's rule now. So then we'll apply L'Hopital's rule to determine what this limit is. So what we'll do is we'll say the limit of x towards 0 of x ln x. So let me write this rather as the simplified version, 1 over x. So this limit, as the limit of this as it approaches 0 from the right, is then equal to the limit of the derivatives. So the limit x approaches 0 from the right the derivative of that is 1 over x, and the derivative of this is minus 1 over x squared. So if we try to simplify this, we'll get a value which is limit of x, limit is of minus x. So if we simplify this, what we are getting then, remember what we did is we wrote this expression as it is over here, and we said that since it has infinity over infinity, then we are able to apply L'Hopital's rule. So we applied L'Hopital's rule here, and we got what the derivative of that is here, and we got what the derivative of that is here. And then what we did is we simplified, and then when we simplified, we're getting minus x. So if we plug in here, we'll get that the limit of this is then 0. So do you see now once again the importance of this L'Hopital's rule, how it helps us? Because we started off with a case whereby we can't determine what this limit is, and then we applied the derivative, and the derivative was then a simpler expression from the one we started off with, and then we simplified to get the limit. And once again, I challenge you to, if you can, use the online softwares to draw this and see whether as this goes towards 0, does it really tend towards 0. So then bear in mind that in this example we chose x to put in the denominator. Then let's just try and find out what could have happened if then we had chosen that, okay, the limit as x tends towards 0 from the right of x ln x. What if we had chosen to keep the x at the top and then the ln x at the bottom? Then if we try to use this expression instead, then we would end up with a more complicated expression than the one we started off with. So then this means it's really important that when you're making a choice as to which of the two graphs or two functions then you put at the bottom, you need to make an educated choice, so to say, so that because the idea behind using this is that you need to have a simpler term than the one you started off with, so that when you do the differentiation, it gives you something simpler. So when we rewrite an indeterminate product, we try to choose an option that will lead to a simple limit. So that's the lesson on this video.